Section 7.1, area between curves, page 2, the final page. So this top area is just restating what we discussed in the previous video, that if you're able to draw the area in between curves as vertical rectangles, because there is a definitive top function or curve above a bottom function throughout the entire range, then we're going to integrate from the left to the right of that interval, where we will take the area from the top function minus the bottom function and simplify to get a single integration function. Otherwise, if we have to revert to horizontal rectangles, because there is no top function throughout the entire interval, or the top function is also the bottom function, then for horizontal rectangles, we integrate from the bottom y height to the top y height, which is why I say dy, and we integrate from the furthest right function minus the furthest left function. And so as I kind of stated a minute ago, when it comes to the limits of integration, it's the variable that's being integrated. And so we need to be sure that we're doing that, the differential, for all of the functions to match. So that's why the top bottom will have a dx and the right left will have a dy. So let's look at example 2. Find the area of the region bounded above by y equals e to the x. So we know that this curve has a horizontal asymptote at negative infinity of y equals 0, and at 0, 1, it kind of starts to shoot up exponentially. But they told us this was the above function, so we knew to draw it here. It's bounded below by y equals 1/2 x, so y-intercept of 0, and then it's, up 1 over 1, 2, to get to our next piece, doing the slope. And they've told us this is the lower bound function, and specifically to integrate between 0 and 1, just this shaded region. This is a 1. We couldn't necessarily shade the area in between the curves because this is going off to infinity to the right, and it's going to be kind of infinity to the left also. We can see there's a visibly top function as we were told. So I'm going to be integrating from the leftmost point to the rightmost point. So from 0 to 1 for my interval. And the top function will go on top, which they told us was e to the x. And we'll subtract the bottom function, which goes on the right side, which we were told is 1/2 x. Now, generally, you would want to combine like terms, but there's nothing to combine here. We can see it's the x variable showing up throughout our integral, so dx is what we're integrating over. The integral of e to the x is e to the x. For 1/2 x, I'm going to keep my 1/2 x, assuming I had a 1 exponent that I add another 1 to get 2. And so I need to take the reciprocal of 2 of 1/2 times this function. And since I did not use substitution, I'm still integrating from 0 to 1. So I can multiply a 1/2 and a 1/2 to get a 4th. And that was the only cleanup that really needed to be done, where first I'm going to find f of b, where I've plugged a 1 in wherever the variable x was, minus f of a, where I've plugged a 0 in wherever the x variable was. So e to the 1 is just e, 1 squared is 1, so I have a minus a 4th. Anything to the 0 power is 1, and 0 times anything is 0. You will notice that I distributed my minus sign to make a plus, but since it's 0, it doesn't matter. So other than needing to combine negative 1/4 with 1, which could be rewritten as 4 over 4, I've got e to the minus 5/4 as my answer. Okay, last example, I'm asked to label the curves. I'm asked to shade the bounded region, which I've already done, so you can actually see it. And then I'm only asked to set up the integrals, but I don't need to solve them because this is more about understanding the setup. So originally you would have just seen these two y equals equations. So seeing that we have a y equals and a y equals, first let's find the bounds on the integration by setting the two curves equal to each other. So this particular y is replaced with 12 minus x squared. The second y is replaced with x squared minus 6. I'm going to go ahead and add this x squared to the right side since it was negative, and since I only have a variable once, I'll go ahead and add the 6 to the other side so that I end up with 18 equals 2x squared, because I can divide both sides by 2 to use the square root property, where I have to do plus or minus the square root of the left side. So I have 2x values over here at -3 and over here at +3. I can see my two graphs cross each other. Now I was also asked to shade, which again, I said the shading's here. Notice I could start shading here between the curves, but there's no bound. I'm going to shade forever. And also I know I kind of need to be in between these 2 points. So I'm not going to shade over here. I'm not going to shade up here. I'm not going to shade over here because all of those are unbounded. But if I go between -3 and 3 and stick from going from one graph or curve to the other, I can see this shaded egg-like oval shape. Now, we can see which is the uppermost top curve from the picture, but again, what if I didn't have that? So what we need to do is just pick any value that's in between -3 and +3. I chose 0 because it makes the math a little bit easier. So I take this first function, I'm going to plug 0 in where x is, and I get a height of -12. So I know I've got 0, -12 on this graph. And now I'm going to take the second equation, and I'll go ahead and plug 0 in where x was, and I get a height of -6. So I've got 0, -6, this point down here at the bottom. So because 12 is larger than -6, that tells me that 12 minus x squared is my top function, and I'm going to put that first. Then I'm going to subtract the smaller height function, which is the x squared minus 6. And we have not previously had to combine like terms, but now we do. I need to distribute the negative sign to have a minus x squared, but a plus 6. And I can take -x squared and -x squared to get -2x, +12 and +6 to get +18. And now I have a single simplified integral from the two intersecting points bounding the original curves. Example B. Might catch your eye that this time I'm given x equals and x equals, but also because we get to see the graph, we can kind of see what's happening visually. But again, be careful. This one doesn't necessarily have a top function, so I'm going to have to use horizontal rectangles. But let's discuss one other piece. We had seen a problem previously where there was not one continuous top function. It was two different functions taking turns being the top function. So we said you could split that in the middle and just solve it as two separate problems. But the key was that area was bounded between two different curves, whereas the problem on the right, area was bounded by the same curve. So you can't subtract a curve from itself, you'll get 0. So in this visual, I can see that the curves intersect here, but you'll notice on the left, the top curve is the bottom curve. And there's portions over here where the right curve is the top and the bottom curve. So even if we try to find points of intersection, we can't break this one into two graphs or curves as we had before. So we're using horizontal rectangles. That means we want to see where they cross, but we want the y value of where they cross. Because we're given that x equals y squared minus 4x and x equals 2y minus y squared, we can set those equal to each other. In this case, I have more than just a y squared. I can also see an individual y that's not going to cancel off. So I don't want to get the y squared alone. I want to get everything set equal to 0. I've got a positive y squared here, and I'm going to take the negative y squared and add the opposite to the other side to get a positive 2y. I'm moving things to the left, so I need to subtract a 2y to the left, but because it was already a negative 4 on that side, I've got a negative 6y. You could try to use the quadratic formula where a is 2, b is negative 6, and theoretically c is 0 because it's missing, but we can also just factor out the greatest common factor of 2y, set that equal to 0 to find out y is 0, and the remaining y minus 3 set equal to 0 would give us y is positive 3. So we can see this height of y equals 0, and 1, 2, 3, we can see this height of y equals 3. So our integral is going to go from 0 to 3. But remember, we need to figure out which is the furthest rightmost function, and without necessarily graphing, although we have the picture in our case, we still may not know which graph is which. So we want to pick a number in between 0 and 3. Even though last time we got to pick 0 because it was an easier math, 0 is not in between these two values, so picking 0 won't be helpful. We'll be picking this point, and they will tie for being the furthest most right function. So I went ahead and picked 2 because it's a whole number. 1 might have been easier. I need to take my first y squared minus 4y function, plug a 2 in for y, and I get a height of negative 4. So over here at y equals 2, I got a height of negative 4. I'm on this graph. Now, taking the second function, I'm going to plug my 2 into that, which is my y value, and I get a height of 0. Well, actually, it's a width of 0, right? So we said when y is 2, we're over here on the x-axis, x is 0, and so we can tell that that is further to the right. 0 is further to the right than negative 4. So that means this second function is our furthest right function, and my first function is the furthest left function. I'm going to head and distributing that negative sign so that I have a minus y squared and a plus 4y. Combining like terms will give me a negative 2y squared, a positive 2y, and a positive 4y is a positive 6y. I've got y's as my variable, so I'm integrating over the y variable.